How you doing, everyone? We're Turning Temple Pervious. I'm Jake Pickering. My partners are Ed Davis and Mark Deal. And for our project, we wanted to design a stormwater management system for Temple University's campus. And we designed a pervious concrete system to go on Palette Walk and an infiltration trench system to go for the roof runoff from the Biology Life Sciences building. Our team leader is Ed Davis, and our advisors are Dr. Felix Udeo and Dr. Robert Ryan. And here's an overview of our pervious concrete system with our block diagram. The runoff from Palette Walk and all its surroundings will go into the porous concrete layer, which will go over into the storage layer, which will travel to the geotextile fabric and infiltrate down into the subbase. We also have a overflow pipe just in case for extreme storm events. And for our infiltration trenches, the roof runoff from the BioLife building will go into a gutter system, over into the pre-filter, which will travel into an infiltration trench, into the geotextile fabric, and will infiltrate down into the subbase. And again, we also have an overflow pipe. Here's a look at Palette Walk right now. This picture was taken on a dry day, and as you can see, there's still flooding going on right around in here, even on a dry day. So the stormwater management properties for Palette Walk right now aren't that great. So we want to transform this into this. What we have here, Palette Walk is slightly regraded, so when rainwater falls on it, it will travel over into the two pervious concrete strips, which are going down next to Palette Walk. And we also have an overflow pipe right here, which will travel into the inlet located in 12th Street. For our project, we wanted to test 3 different batches of pervious concrete. We decided to have a different water cement ratio for each batch. One would be 0.27, another one would be 0.30, and another one would be 0.40. And if you look to the right over here, you see the different layers for our pervious concrete system. On the top we have the porous concrete layer, followed by number 57 stones. That's a storage layer for the rainwater when it travels through it. We have the overflow pipe located in the middle, and surrounding the number 57 stone would be a geotextile fabric with the subbase soil located below that. As for our infiltration trenches, we didn't have a lot of space to work with surrounding the BioLife building, so we had to make do with what we had. So we decided to divide the rooftop area into 2 different areas. They would each travel to their own respective trench. Infiltration trench number 1 will get this rooftop area right here, and the second one will get this rooftop area right here. And what an infiltration trench is, basically it's a large hole in the ground filled with number 57 stone. It's surrounded by a geotextile fabric, and below that is the subbase soil. And there's also an overflow pipe, just in case. Here's a look at our first prototype we made. On the left is the infiltration trench system, and on the right would be the pervious concrete system. For the infiltration trench, we have the gutter system, followed by a layer of soil on top, and this soil you can put in flowers or something to make it look pretty. We have the geotextile located below that, overflow pipe, number 57 stone, and then another geotextile on the bottom. And for the pervious concrete, we have a layer of pervious concrete, the overflow pipe, the 57 stone, and the geotextile on the bottom of that. And here's a look at our completed first prototype. And for our second prototype, we want to add soil into the bottom of our, we're going to design something similar to this, but we're going to have soil located at the bottom. Because when we ran water through this one, the water immediately went through it and out the bottom, which isn't really realistic because the soil in the bottom, once it becomes fully saturated, it would allow the water to back up through the number 57 stone and eventually pour out of the overflow pipe. So we want to find those accurate infiltration properties. In addition to our prototype, we also have a SWIM model. SWIM is a rainfall simulation program. We'll be able to simulate different rainfall events on our system, like 110 years of the past rainfall events, including a 2-year storm, 100-year storms, hurricanes, all that fun stuff. And from these different storm events occurring on our system, we'll be able to determine the different infiltration values, amount of water overflowing, and if there's any flooding in our systems. Now for the test results. When we broke open the 0.27 water cement ratio, molds, it completely fell apart. We weren't able to test any of them because it was basically just rocks. It's a pile of rocks. So for the .30, we had a 28-day compressive strength of 2,030 psi and a void content of 20.68%. And for the .40, we had a 28-day compressive strength of 4,540 psi and a void content of 19.16%. And over to the right over there is just a picture of us doing the compressive strength test. Here's a look at the stress versus strain graphs for the .30, which is on the left, and the .40 on the right. For our design, we're going to utilize a .37 water cement ratio, and we chose to do this because the difference between the compressive strength for the .30 and the .40 was 2,510 psi, and the difference in void content was only 1.52%. So while we could go in the middle just with .35, we wanted to get a little bit more of the compressive strength since we wouldn't really be sacrificing much of the void content at the same time. So that's why we chose to go with .37. We also performed a sorptivity test on our pervious concrete. For the .30 water cement ratio, we got a 7.492% absorption rate, and for the .40 water cement ratio, we got a 5.223% absorption rate. And these are values that are rather low for pervious concrete, which is a good thing because then there's less chance for freeze-thaw problems to occur with the pervious concrete. We also performed a flexural strength test on the pervious concrete. The .30 had a 407 psi, and the .40 had a 788 psi. Both of these values are within 10 to 20% of the compressive strength, so both of these values pass the test. And to the right, again, it's just us doing the flexural strength test. We obtained a soil sample from next door to the engineering building, 10 feet below the surface at the construction site currently going on. And we performed a falling head permeability test on it. We determined that the hydraulic conductivity is 2.332 centimeters per hour at 20 degrees Celsius. And we determined that this is similar to a very fine sand silver loam. We also performed a liquid limit test on our soil. We determined that the liquid limit is 8.290%, and we also classified the soil. And by doing these two tests right here, we determined that the soil is a silty sand with some gravel in it. We also performed a drying time test on the soil. Basically, with the drying time test, we got a sample of soil, fully saturated it, then we let it dry, and we came back and we measured it once a day to see how long it would take for the soil to dry. And we determined that it would be 90% dry after 13 days. What we could do with this drying time and the hydraulic conductivity, we could plug these values into our SWIM model so we can have truer to life values for infiltration, overflow, and all that stuff. Here's a look at our SWIM model. To the right here is our actual SWIM model. We have, right here is the BioLife building. The top half is going into this infiltration trench. Bottom half is going down into this infiltration trench. And right in here is the pervious concrete system on Plug Wall. And we simulated the past 110 years of real rainfall data that occurred in Philadelphia onto our system here. And after you simulate that, it'll give you these results located right here and right here. And since they're a little tough to read, we put them in these tables for you. First, we ran the simulation with the default infiltration values that SWIM gives you. It was a total amount of rainfall of 194,000 inches on all of our systems put together, which resulted in 98.4% infiltration and 1.6% outflow to the combined sewer. And then after we put in our infiltration values, our drying time, we ran the simulation again, and we determined that we had a 98.7% infiltration and a 1.3% outflow to the combined sewer. And this just takes a closer look at each of our systems separately. For the first infiltration trench, there was 100% infiltration with 0% outflow to the sewer. For the second infiltration trench, again, there was 100% infiltration with 0 going to the sewer. For the pervious concrete north strip, there was 99.8% going to being infiltrated into the ground, with 0.2 being outflow. And with the southern pervious concrete strip, it was 94.8% infiltration with 5.2% going to the outflow. And the reason that it's all going to the majority of the outflow is in the southern pervious concrete strip is because the overflow pipes for all the other systems are all connected into the southern strip. So the southern strip is getting the overflow from the whole system all as a whole. So taking a closer look at a 2-year storm. A 2-year storm occurred in Philadelphia on August 12th, 1955. And for a 2-year storm, there was 136 total inches of rainfall. Of that 136 inches of rainfall, 136 infiltrated into the ground. So we had 100% infiltration with 0% outflow. And this is actually good because our design constraints, we wanted to design our system to be able to fully infiltrate a 2-year storm. What a 2-year storm is, if you don't know, it's a storm that will occur once in every 2 years. Here's a graph of our 2-year storm. The red line you see here is precipitation, and the green line is infiltration. And you can see the infiltration graph directly mirror the precipitation line. And the only reason it's pushed to the right is a little bit is because it takes a little bit of time for the water to infiltrate into the ground after it precipitates onto the system. Here's a look at Hurricane Katrina. During Hurricane Katrina, 241 inches fell on our system, 215 of which got infiltrated back into the ground, which gives you an 89% infiltration rate. And 27 inches went to the 27 inches went to the outflow combined to the combined sewer system, and 11% would be outflow then. And here's a look at Hurricane Katrina. Again, the red line is precipitation, the green is infiltration, and this new line over here, this pinkish purplish line kind of thing, that's outflow to the direct sewer, to the combined sewer. If you notice early in the morning here, there wasn't a lot of precipitation going on, so a lot of all of the precipitation infiltrated back into the ground. Until we got over here at this huge spike of precipitation, this means that it rained a lot over a course of just a few hours here, and that's why our overflow pipe had to be used, because our system got a little overwhelmed. And as you can see, the infiltration also went down, because the rest of it had to go to the sewer. Here's a look at Hurricane Floyd. This was the biggest rain event that occurred on Philadelphia in the past 110 years. 281 inches. There's 281 inches of rainfall on our system, 265 of which got infiltrated back into the ground. This gave us a 94% infiltration rate, and we had 6% of the water going to the outflow. And this is actually interesting because Hurricane Floyd rained more than Hurricane Katrina, but it actually used the outflow pipe less. And the reasoning is on this next graph. As you can see, it gradually, the precipitation gradually builds up and more gradually builds down. There's not that giant spike that was like Katrina. So the overflow pipe was used for a longer duration, but it doesn't have that big spike in it. Here's a look at a histogram of all the rain events that occurred on our system over the 110 years. The bar to the left here, 54%, and that stands for 54% of all rainfall was 0.2 inches or less on our system. And we wanted to capture the first inch of rainfall because then we will be able to get PWD stormwater credits to help fund our project. And the first inch of stormwater is right here. So we need to capture all these bars, which equals around 91%. But after performing the simulation on our system, we found that we caught 100% of all rainfall events, with only the events right around down here producing any outflow at all. In the next couple of weeks, we want to try to make the system a little smaller to help reduce construction costs. And we'll do this through a trial and error basis. We'll make the system a little smaller, run the simulation again, and see if we get adequate infiltration values and all that still. And we'll do this until the system no longer meets our constraints. Here's a look at the financing and cost of our system. The total cost of our system would be around $37,500 after plugging some values into an equation found on the Philly Water Department website. we determined that Temple would save $164,000 after 20 years. So taking into account the construction costs, they would begin to save money after about 4 years. Some risks involved in our project. The underground utilities, when we're implementing it, we don't want to be running into the electrical wires underneath the sewer lines, because then that would just cause our construction costs to go way up. We have to take into account the soil infiltration properties. We also have to make sure we're performing the right construction techniques, and we have to have the proper maintenance occur in our systems from here on out, because if this proper maintenance isn't given to the systems, they'll become clogged, and then they'll be rendered pretty much useless. Some possible drawbacks for our system are there might be small inaccuracies with SWIM. The soil specimens for the test weren't taken from the actual construction site that we'll be performing at. They were taken from the construction site next door. And if there's improper installation going on when we're implementing the project, that would also be a drawback. And for the future, for the next couple of weeks anyway, we want to construct our final prototype. We want to test the smaller size systems for SWIM. We want to have a meeting with Temple Facilities regarding actually implementing our project. And we also entered the EPA Campus Rainworks Challenge, which we'll be able to see the results for that on April 22nd. And are there any questions?
Well, the strength of your concrete, the pervious concrete, can you go back to that? Well, you said for the 0.3 water cement ratio, you had a strength of 2,030 psi.
Mm-hmm.
And for the 0.40, you have 40 psi. That doesn't seem to follow this trend.
That's what we found originally too. We think that this one had a lower compressive strength because it didn't have, because since the 0.27 completely broke apart, this one might have been kind of close to breaking apart. So that's why it failed at an earlier strength. When if we made it more at like a 0.37 or 0.35, it would be able to hold more of the weight.
Well, I think you still have to find better reason to explain that, because you can see the smaller the water cement ratio from the normal trend, the higher should be the concrete strength. That's the trend.
Mm-hmm.
So if you're having 0.3, you're having 20, 30, and then 0.4 you're having is the other way around.
Mm-hmm.
So from your concrete knowledge of concrete, the higher the water cement ratio, the lower the strength.
Yeah, that's
also,
what
okay.
we found that through research, and we
Then you have to check up that again.
Yeah.
There's a problem there. Now the second one, you do test the hydraulic conductivity of the pervious concrete itself.
We were going to, but we found out that the results of that test would basically give us the void content. Well, they would give the hydraulic conductivity, but when we would perform tests on when we would perform like standardized tests on it, but we would pour water on our pervious concrete samples, and it would immediately go through. So the like doing a falling head test on it would be hard, because you have to like because it has to get clogged and backed up for it to, because then you have to release the bottom valve and for it to fall through it. And as soon as you release the bottom valve, it would just all go dumping right through it. Which isn't a bad thing, because we have, since the void content is towards the higher end for pervious concrete, it's we have a high infiltration value.
Yes, you have that. In fact, you can fabricate, you can devise something.
Mm-hmm.
We've had it done before.
Yeah, we
To
can.
test the hydraulic conductivity. It's very important to test that.
We can actually test it on these cylinders here if we just get like a pipe at the exact diameter of it.
Yes, you can have a pipe and then you close the sides.
Yeah, with like a
So
gum
no water can
kind of.
and then you test that.
Mm-hmm.
It will be very interesting to know what it is.
Mm-hmm.
In fact, if you observe that the trend is going to be the same, the normal trend,
Mm-hmm.
where you have the 0.4 is going to be more pervious. The permeability is going to be higher. Why? Because there will be more void in it.
Mm-hmm.
You know, so you need all that. Do it just there. All right, that's just mine. Those are my observations about it.
Questions?
I was just gonna comment on point two. I don't think your result is accuracy is a liar. The reason is when you deal with 0.3 water cement ratio, you have to look into your workability. And I'm very sure when you did this, you did not look into that. The workability was very low, and that's why you ended with a low strength. If you have added a plasticizer or some additive like an air train,
We actually-
will have increase your workability and your compaction of your cement.
We actually added these admixtures in there. Maybe we could add a little
You
more.
have done something wrong in the mix. It's something wrong.
Okay.
Your workability is not. Did you measure your workability?
We did that through the void and then the void content and density. It's a new test designed by ASTM.
Yeah, but Dr. Udo is very correct. 0.3 cement, 0.3 water cement is a preferred water cement ratio if you do it right,
Mm-hmm.
and you get a much higher strength.
Okay.
But your result, you have enough time.
You have to check that off, as told you before.
Yeah, we
There's
will.
a problem there. You are going for competition. By the time you present that, they'll be wondering, what's Stanford doing? What are we teaching? All right, so you have to check off that, make sure that it follows the trend.
Mm-hmm.
Yes.
Other questions?
Just curious, what's sorptivity?
That's a absorption rate of the concrete. Basically, it's water that gets absorbed into the concrete, and it's for porous concrete. It'll be higher since it has all the holes in it.
It kind of just stays there.
Yeah, but for hopefully it would go back out since it is porous, and it would drain back out. Yeah. Mm-hmm.
I get it.
Okay, I've got one last question, then we have to move on because we're running behind. And go to your swim results, please. You talked about your 2-year storm and Katrina and Floyd. Pull up go to that previous slide.
Oh, okay.
136 inches of rain. Can you explain what, because clearly 136 inches of rain did not fall out of the sky.
Oh, that's over all of our systems as a whole. That's it's not 136 inches like high. It's just over our over the area of our systems, over the rooftop area and the pullet wall.
136 inches of rain fell on the rooftop?
Well, this was during a 24-hour event too.
Which is about 2 inches of rain in this area, 3 inches of rain in this area.
Yeah, it's 3.3, I believe.
So how did you get the 136?
We ran, we determined that it was from this date right here, and we ran the simulation just on that date.
Right, but 136 inches of rain did not fall out of the sky. So my question is, if only 3 inches of rain fell out of the sky, where does 136 inches come from?
The 136 is these numbers right here added up.
Okay, where did those numbers come from?
That was from this is the results for just running this day.
But again, 50 inches of rain didn't fall out of the sky.
It looks like the total.
Please.
Yeah,
Okay, so that's something you just need to
yeah,
to work
we'll
on
look
that.
into that, yeah.
And it has
I'm
to
not
do
sure
with
why, 'cause
the
I
total
understand, yeah.
area that the rain fell on
Mhm.
and the total area that's capturing the rain.
Mm-hmm.
Okay, so we can
Okay.
talk about it later, but
Okay.
that's a big deal. All right, that's about all we have, thank you.
It's a storm that'll occur once in every 2 years.
Why it's still not 10?
Not 10? Well, it's based on a lot of, it's based on an average of all this rainwater that's ever fell in Philadelphia.
So
Oh, why just because that's what we made our design constraints for. We wanted to
if you want to
capture.
increase the number a year, you have higher probability, higher value.
What's
I
that?
don't think anybody has designed anything for 2 years.
Well, we have our system actually caught everything, even during the hurricanes still.
So you weren't designing for 2 years.
That's what we.
I looked at the 1955,
Mhm.
and you're designing for 2 years. Does that make sense?
That date is just the date of that a 2-year storm occurred in the past.
Well, we actually need to
10
move
years.
on, so I think you're off on the wrong track. The 2-year storm is a regulatory design storm. By regulation, your system has to handle a 2-year storm. It also has to handle a 10-year storm and a 100-year storm. So that's just one
That's what I'm
regulatory
concerned.
issue. Yeah.